In today's talk, we're going to talk about relative risk and odds ratios. These are statistics that are used when the data are discrete. That is, you have a disease or you don't, you have a risk that exists or it doesn't. We'll begin by defining things like incidence and prevalence, relative risk and odds ratio are measures of effect size, that is, the relevance of these things. We'll define them. We'll look at the relationship between the two. We'll see some of the advantages and disadvantages of using odds ratios. I would like to start with an example. This actually isn't something you can do in your practice because it's sticking a needle in your eye, which you can do, but for this particular one, it's VEGF, it's a drug, and it's for macular degeneration. I'm just going to call it PEG, pegaptinib. We'll say PEG. It is a drug that blocks the development of growth hormone that increases small blood vessel growth. And in this randomized controlled study that they did, they used the drug or a sham. People were randomly assigned into one group or the other. There were 295 subjects in each. Now, I mentioned that that it's a discrete thing, and so we're going to look at letters lost, which is not discrete, it's kind of an interval data, but they break it into two groups. Letters, if you lose less than 15 letters, which is about 3 lines, or you lose more than 15 letters over a period of a year. This table is kind of a condensed version of the paper, and it's a summarized table that I got out of a book, but the actual paper is available too. So let's look at this table. So the treatment of PEG, there were 295 subjects. 206 of them lost less than 15 letters over a year. That's a good thing. To lose less vision is good. For the sham, it was 164, and the same number, so the sham did not do as well. Now, the question is this a reliable result? Are these numbers distributed by chance? And so what we do is we look at chi-square, this statistic called the chi-square. We'll get into odds ratio and relative risk in a minute, but right now they just tell you the magnitude of the effect. The chi-square tells you if chance is a reasonable alternative. We see here that the chi-square was 14, p less than 0.001, so the probability of finding a chi-square of 14, if the null hypothesis is true, is not very good. So we would reject the null hypothesis and say that this difference is not a result of chance. The chi-square, let's just talk a minute about that. We see the formula here. It's the sum of the observed minus expected squared over expected. Observed are the actual numbers, the 206, 88, 164, 132. And it's important to realize that this is in the context of the marginal totals, which are 295 for each of the two groups, and then in the outcome 370 and 220. And these come into play when we calculate expected. So when we talk about what do we expect by chance, we consider these marginal totals. And the way you do that is, for example, to come up with the expected value for the observed 206, it's the column total, 370, times the row total, 295, divided by the grand total, 590, equals 185. So we saw 206 we would expect 105 by chance. So there are actually more observations in the PEG group that lost fewer letters than we would have expected by chance, which is why we would probably conclude that this is an effective drug, because its observed number was higher than expected. So let's just take a moment and think about incidence and prevalence. Incidence is the probability of an event initiated within a given time period. For example, the number of children who develop myopia at age 7. So there is a clear study. I'm not sure if you've talked about that in other classes yet, but it's a longitudinal study, looks at the development of myopia. They get kids and they start out and they look at children who do not have myopia when the study starts. And then they look and they measure them each year, and the number of children who develop myopia at age 7, the percent of those who develop versus those who have not developed it, who have not had myopia before, that proportion is called the incidence. The prevalence is if they looked at kids at age 7 and they said how many kids who are 7 have myopia. And it doesn't matter when they developed it, it's just that when they measured at age 7 the kid had myopia. That proportion is called prevalence. So in our example, we look at the number of AMD patients who lose less than 15 letters over a year. That's kind of an incidence. Okay, relative risk. In this statistical question, we are interested in relative risk. It's the risk of an outcome in one set of conditions relative to the risk of an outcome in another set. We usually use the control group as the point of reference by putting it in the denominator. And so we look at, and that would be the sham group, for example. So we look at the effects of treatment, the risk of developing AMD in, or advancing your AMD in terms of losing letters in the treatment group relative to the control. Relative risk allows us to judge clinical relevance. So we had, is it a reliable result? Now we ask, is it a relevant result? And this is a randomized controlled trial, so we can actually directly compute relative risk. We use odds ratios when we cannot directly compute relative risk. We want to know relative risk. We estimate it with an odds ratio. Talk about that in a minute. So what is the risk of, or really, you can look at it, the risk of saving your vision over a year, or the risk of losing more vision over a year. The risk of saving your vision is kind of a weird thing to call that a risk, but it's 206 divided by 295. And if these two numbers were equal, if it was split 50-50, there would be no advantage of using the treatment. It would be 50%, or well, the risk would be 50%. But since it's less than 1, that means there is an advantage over that 50-50 cutoff. The success with the sham is 64 over 295. That's also kind of a low number. But the question is the relative risk. So what's the probability of success with treatment versus the probability of success with sham? And so that's 0.7 over 0.55, or 1.27. So you have a 27% greater chance of losing less letters if you get the treatment. So relative risk is the ratio to incidences. It could be also the relative the ratio to prevalences. It doesn't really matter. But in this study, we're talking incidences. Now, the odds ratio is another way of measuring relative risk. It's an estimate of relative risk. It's most frequently used in case control studies when we cannot compute relative risk. And it's also best to use when the event of interest occurs less than 10% of the time, and we'll see why that is. So, how do you calculate the odds ratio? Well, in this particular example, we can calculate relative risk, and we would do it if we were presented with this table. So when we calculated relative risk, we took 206 and divided by 295. The problem comes in the outcome, and we'll see an example of this in a moment, but this is kind of how bad is the disease state. And in a case control study, we choose our cases and we choose our controls, and so the total is kind of meaningless. So you can't, because we fixed the total number by the way we selected our subjects. In this case, that isn't the case because we have randomly assigned people into the groups and we just look and see how it happens. But we're going to calculate odds ratio in this context just so you can see the difference between the two. So 206 in relative, the risk was 206 divided by 295. In an odds ratio, we can't use this number. So instead of going across, we go down. But also, the total number doesn't make much sense either. So we get kind of what is the number we would expect if there was no treatment. So how well would we do in having less letters lost in this group if we divided 206 by 164? The same way over here, greater letter loss, it's 88 divided by 132. So we have these odds. Given that you lose less, what are the odds that you had PEG versus sham was 206 to 164. The odds of doing poorly in terms of letter loss was 88 to 132. So we take that, we divide the 206 by 164, and we divide the 88 by 132, and then we divide the one by the other. So we divide the good outcome by the bad outcome, we get 1.88. So that is our that is what we got. We're not going to compute confidence intervals in this class, but you will often see confidence intervals reported. In this case, the confidence interval for the odds ratio is 1.34 to 2.64. Now, what does that mean? Well, an odds ratio or relative risk, when it's 1, it has no effect. The ratio of whether you're talking about relative risk of letters lost over sham, if they're the same, if those risks are the same, then the ratio is 1. If the odds are the same, the ratio is 1. But we have computed confidence intervals around our 1.88, and we notice that the confidence interval does not overlap 1. It's important that it does not overlap 1 because that means that chances are pretty good that the null hypothesis is not true. And you remember from our chi-square, we got a chi-square of 14 with a p equals 0.001. And here we see that the confidence interval also does not overlap 1. The confidence interval will always be consistent with the p-value. So 1 is no effect in both odds ratio and relative risk, and a confidence interval that doesn't overlap 1 indicates significance. So, odds ratio versus relative risk. The effect size of interest is the risk of one condition given baseline. This is measured directly by relative risk. The odds ratio is an estimate of relative risk. So if I ask you to estimate relative risk and you can do it directly, then you would do that, and if not, then you would look at the odds ratio. And sometimes people, when you read your papers, you will see that they have calculated relative risk when they should not have, because it was a situation where there's odds ratio. And so they kind of underestimate the actual effect. This doesn't happen very often. Usually reviewers are pretty good at picking that up, but just so you know, it can happen. Relative risk can be measured in groups that are randomly assigned, or in cohort studies like the CLEAR group, where the outcome is not predetermined at the outset of the study. In our study, it is most appropriate to compute relative risk, the example we've done. In case control studies, it's based on collecting the outcome first, finding cases and matching controls, and then looking to see what caused them. Because the numbers of outcome events were predetermined, they cannot be used to compute the relative risk. So we use the odds ratio. Okay, here's an example that we actually talked about earlier in the course. It was a paper on AMD, and this is one of the measures that was tested. So, for example, we had a number of AMD patients, and then they found controls. Now, these numbers are not equal. That doesn't mean that they weren't selected. So basically what happened was the investigators picked out a certain number of people. They were able to get 137 after selection and 369. My guess is they went for a 3-to-1 ratio, and they just didn't quite get as many controls as they had hoped. There was missing data or something. So here we see that our odds ratio is 30 over 107 divided by 101 over 268, or 0.74. So what does that mean? It means that you're actually 26% less likely to get AMD or advance in your AMD if you have high cholesterol. Then if we look at the confidence intervals, we see that the confidence interval is from 0.47 to 1.2. Now this range overlaps 1. So we cannot rule out chance as a reasonable alternative. So even though the odds ratio was less, we have a significant, or we don't have a significant relationship between them. So with OR, now here's an important point. OR is less than 1. So high cholesterol is protected. When the number is less than 1, it's protected. When the number is greater than 1, it's a risk. And so one thing that we need to point out, it's very important, is that the odds ratio always overestimates relative risk. In our example, relative risk was our example with the PEG. Our relative risk was 1.27. The odds ratio was 1.88. That is an overestimate. And that's because you couldn't really tell. It was kind of a 50-50 odds ratio, or a 50-50 prevalence, because it was evenly distributed. So it was a little higher. Now, in this graph, what I try to show you is that the proportion of events. So, for example, AMD is really low frequency, say 3 to 5%. Myopia is a much higher frequency depending on where you are, somewhere between 25 and 80% probability. But the odds ratio with exactly the same numbers just gets bigger and bigger and bigger, whereas relative risk does not vary depending on the proportion of risk of events. So this is what we mean by an overestimate. Now, it is also important to point out that when the numbers are less than, when the odds ratio and the relative risk are less than 1, it's more extreme, and it's the more extreme value from 1. So a smaller proportion is more protective. But if it was, say, the relative risk was 0.8, then the odds ratio would be a number less than 0.8. And even though we're saying overestimation means further from 1. So 0.1 is a much greater overestimate than 0.8, even though the number is smaller. There are many cases where relative risk is the appropriate method. In the CLEAR study, for example, is a longitudinal study. It's very appropriate to calculate relative risk. The problem is that if you want to adjust for other variables, then you have to use logistic regression, or one way is to use logistic regression, and that allows you to estimate the odds ratio. So for example, we have this is a regression equation. Y is discrete in this case. We talked about y being a continuous variable in multiple regression. In logistic regression, this is yes or no. I got myopia or I didn't, as a function of multiple variables. And we're not going to go too much into how you compute the logit, which is basically the natural log of the probability and one condition of getting myopia over 1 minus that probability. The point here is that when people write papers and they adjust for multiple variables, they're using logistic regression. But they're exponentiating they're exponentiating the coefficient, this little regression coefficient. It's 10 to a power. Well, no, it's e to a power. And that gives us the odds ratio. So one thing you have to keep in mind is that when you look at, if people don't make a mathematical adjustment to relative risk using prevalence, which they almost never do, then the odds ratio is always an overestimate. So when you look at the CLEAR study, for example, the CLEAR study papers, and they have many of them, they're reporting odds ratios. And because myopia is pretty frequent, those are pretty much overestimates of the actual value. Now, significance is still the same, but the estimation gives you a sense that it's more than it should be. Here's an example where we have, this is the y equals a plus bx, so this is the constant, 0.21. This is the treatment coefficient, 0.64. When you raise it to an e, you get a 1.9. So what that means is whatever this treatment is, it's about 90% more effective than the control. I'm not going to go into this much more than that, but let's see that. So chi-squared tells us how reliable our results are in terms of consistency of a real association between treatment and control. Similarly, the confidence interval does a similar thing. And relative risk and odds ratios tell us the clinical relevance in terms of the magnitude of effect of the treatment. So if you have an odds ratio at relative risk of 2.0, then you're twice as likely to get the disease or as a function of the risk. And if your relative risk or odds ratio is 0.5, then you are half as likely, 50% less likely to develop the disease. All right, that's it.